Hey, today we're going to do a quick number theory problem that absolutely kicked my ass. Here's the problem. Write 1 to 100 on a board, take two numbers A and B from the numbers you wrote, and replace it with the GCD of a squared plus b squared plus 2 and a squared b squared plus 3. Repeat this process till you have one number left. And the goal is to prove that the last number is not a square. To kind of just exemplify this process, let's look at a much smaller example with, say, 1, 2, and 3. Well, here, if I say take these two numbers, 1 and 2, as A and B, what I'll get is I want the GCD of 1 squared plus 2 squared plus 2 and 1 squared 2 squared plus 3, which is going to be equal to g of 1 plus 4 plus 2 is going to be 7, and this is 1 times 4 plus 3, which is also 7, which is equal to 7. So then that cancels these out, and we end up with 7 and 3. And then now we're going to do the same process again, which gives us GCD of 7 squared plus 3 squared plus 2 and 7 squared 3 squared plus 3. Well, this is equal to 49 plus 9 plus 2, and this is going to be equal to 49 times 9 plus 3. And maybe do some quick maths here. We're going to have the GCD of, 49 plus 11 is going to be 60. And we could do this as 49 times 10, which is 490. 490 minus 49 is going to be 441 plus 3, which is going to be 444. And well, I know in this I have a factor of 3, and I also have a factor of 4. And in this one, I of course have a factor of 4. This is going to be times 1, 1, 1. And this, of course, is divisible by 3, since the sum of this is equal to 3. So together, that's going to be equal to, well, it's going to be 3 times 4 here, which is equal to 12. So my final remaining number is going to be 12, and as you can see, not a square. So I'm going to be walking through my intuition and how I solve this problem. When you first look at this problem, maybe if you try a few small cases like I just did to gain some intuition about how things work, the first thing I think you can notice is these two functions, if you squint a little bit and put them side by side, it kind of looks like a polynomial, and that it feels like there should be some relationship here. Some people that have experience with number theory will find this wholly unnecessary. Maybe they've already done problems like this in the past and stuff like this, or they're just really brilliant or something. But when you see a bunch of squares, a really good step to take is to look at things mod 3 or mod 8. This is basically due to Fermat's little theorem. So mod 3, if you have anything that's co-prime to 3, basically, the square is going to end up being congruent to 1. And if you're looking at mod 8, the squares are all going to be 0, 1, or 4. So you can heavily reduce the number of possible options and stuff. There's kind of this intuition that people might have, but for me, this is the first time I'd worked with a concept like this before, so or with these types of functions before. So I'm going to show you kind of the underlying work that would go into developing the intuition to be able to just see that and go, okay, let's look at mod 3. So when I looked at these functions, and you try to like think about what's going on, in order for a GCD to divide both things, like let's say you have here, this is your first number, number 1, and then this is your second number, number 2, and let's say this is 0. In order to divide both of them, well, you're going to have to divide the first number, obviously, and then you're also going to have to divide the second number, but in order to divide the second number after dividing the first number, what you're really doing is you're dividing the difference. And this is like key, because as we'll see when we take the difference. So let's try that. We'll take a squared b squared plus 3 minus, that's our second number, minus a squared plus b squared plus 2. And well, this is equal to a squared b squared, plus 3 minus a squared minus b squared plus 2. And well, of course, this can cancel out into plus 1. And then we can factor out the a squared here to b squared minus 1. And this is going to be minus b squared here. Well, this is equal to b squared. If I factor out the negative here, it's going to be equal to b squared minus 1 over here. And this also has a b squared minus 1. And then we can factor out the b squared minus 1 from this. So this is equal to a squared minus 1 times b squared minus 1. And of course, everybody has learned this in probably middle school or maybe high school. This factors into a plus 1 times a minus 1. And this one is b plus 1 times b minus 1. Right, which is very nice looking, that the difference ends up in this highly factorized form. And now you can kind of see where the mod 3 intuition comes from, because if I just kind of like imagine my b is here or my a is here, well, this plus 1, b, and then minus 1, this kind of spans 3, right? Because if you think about it like this, it's going to be like b minus 1, b, then b plus 1, and one of these has to be divisible by 3 because it's every 3 numbers is divisible by 3. When I first saw this, there's kind of 2 directions you can go. You can either do mod 3, or I was thinking maybe mod 2 because there's a symmetry between the a and b side. Turns out the mod 2 idea doesn't really go anywhere, and actually this kind of screwed me up later, but the mod 3 idea is the right direction. So let's call this function that we factored out here, this expression here, let's call this 1 star. Before we get to the part about proving stuff, let's also prove one property that we can get immediately almost from exploring this difference. It's so nice, so there must be some stuff that can work well later down the line, I think. And the way this works is we're going to call this 2 star. Imagine you have any factor, d, which divides both the a side and also the b side of 1 star. Okay, if this happens, and it's also a factor of both of the functions, so d is also dividing the GCD, well, what's going to happen is, let's just look at this here. Because it divides both sides, and it divides the GCD, it must divide one of these 2 functions, one of the original 2 functions. I think a squared plus b squared plus 2 for me looked a little bit nicer, since the a squared times b squared getting just lumped together like this is pretty hard to work with. And in fact, it is much, much easier to work with when you have these 2 separate functions that you can kind of manipulate into this. So you can rewrite this as a squared minus 1 plus b squared, this first function here. You can rewrite it as a squared minus 1 plus b squared minus 1. And since I took 2 1s out, I have to add them back to the 2 plus 4. And Well, what do I get here? Since I know if D divides this already and D divides this already, right, from these two, well, they kind of go away. So now I know D must divide 4, which gives you that D has to be 1, 2, or 4. Right, so this is the key property here, that if D divides both sides of 1, it must be 1, 2, or 4 if it's also a common factor. As I mentioned earlier, since we're going to use our intuition for this mod 3 idea, and the problem doesn't tell you anything about the order of how you're applying this operation, there has to be some sort of invariant that is maintained as you remove numbers from the board. And since we're looking to prove that the last number is not a square, you want to find an invariant that somehow shows you there is one unpaired prime, at least, in your final number. So wouldn't it be nice if that final prime was 3? So the very nice way to look for this invariant, we're going to call this operation where we take A and B and then replace it with a GCD. We're going to call that operation F, okay? This is going to be the operation. And if we're asking about things mod 3, well, there's kind of only 3 cases. There's 4 cases because A could be a multiple of 3 or B could be a multiple of 3. But A and B in these two functions are symmetric, so it doesn't matter which way it's without loss of generality, you only have to show one is a multiple of 3 and the other isn't a multiple of 3. Those cases are the same. All right, so there's actually 3 cases that we want to look at and see what happens to the GCD. So here, what we're going to do is we're going to look at these 3 cases. Case 1, A is a multiple of 3, and B also is a multiple of 3. Case 2 is A is not a multiple of 3, and B is not a multiple of 3. And by the symmetry that I just said, we're going to look at this last case, case 3, where let's say just A is a multiple of 3, but B is not a multiple of 3. And this is all the cases. So what happens if A and B are multiples of 3? Well, if A and B are a multiple of 3, again, let's look back at our picture here. This is A, and this is a multiple of 3. Since every 3 numbers is divisible by 3, I know that this is not a multiple of 3 and this is not a multiple of 3. These don't work, right? And this happens for both A and B. So this implies that in 1 star, since all of my factors are, well, A plus 1, or A plus 1 and A minus 1, and then B plus 1 and B minus 1, that basically A plus 1 here and A minus 1, neither of these can be multiples of 3. And this is the same for B plus 1 and B minus 1. So none of these, all of these are not multiples of 3. And that implies that since any factor of the GCD has to divide this difference, that implies that the GCD is also not a multiple of 3, since 3 can't divide the difference. Now let's look at the case where both a and b are not multiples of 3. Well, in this case, again, we look at the same picture, right? I have a and b here. I know at least one of these has to be a multiple of 3. The reason is because, so let's take a look. Imagine if a was, let's say a mod 3 is equal to 2. Well, I know that then a plus 1 is a multiple of 3. This is like a mod 3. This is the same. This means the same basically. It's just a notational difference. And the same case is like, what if a mod 3 is equal to 1? Well, in this case, then a minus 1 would be congruent to 0 mod 3. Okay, so we've basically established that if both of these are not multiples of 3, at least one of them, either a plus 1 or a minus 1, one of these will be a multiple of 3, and the same for b plus 1 and b minus 1. At least one of them will be a multiple of 3. But remember, based on 2 star, anything that divides both, so on both sides here, I know 3 is going to be on this side and on this side. If it's also in the GCD, it can only be 1, 2, or 4, which then tells you, well, 3 is not equal to 1, 2, or 4, does not equal 1, 2, or 4, so GCD mod 3 cannot equal to 0. The last case here is only one of them is multiple of 3. So, or this one is the multiple of 3. So in this case, if we look at our a plus 1 and a minus 1, we know that neither of these can be multiples of 3, but at least one, b plus 1 or b minus 1, at least one of these are multiples of 3. So when this happens, what we know then is we have that 3 divides b squared minus 1, but 3 does not divide a squared minus 1. And in order for 3 to be in the GCD, well, remember, 3 can't just divide the difference, it also has to divide at least one of the two numbers that you're looking at for your GCD. And in this case, again, it's just a little bit easier to work with a squared plus b squared plus 2 because we have these two functions where the factors of a squared and b squared, or not the factors, sorry, the terms of a squared and b squared are separated and not multiplied together. So if we look at this, so what happens? Well, we have a squared. We're going to try to write this type of stuff similarly. We know b squared minus 1 can be divisible, and since we did this extra minus 1 here, let's add it back to the 2 that's from over here, and we'll get a squared plus b squared minus 1 plus 3. Right, so the question is, does 3 divide this, question mark? Well, we know 3 divides b squared minus 1, so this gets canceled out, and then that's going to equal to a squared plus 3. And here, well, we know a originally from our case divides, 3 divides a. So that means that you can write a is equal to some sort of like 3 times x, for example. And therefore 3x squared plus 3, well, this is congruent mod 3 to 3 times 3x squared plus 1. I just factored out one of the 3's, and well, this is of course congruent to 0 mod 3, which means that, oops, not 3 there, sorry. This is, of course, meaning that the GCD, since 3 divides this a squared plus b squared, this is technically plus 2 minus 1 plus 3, and also it divides the difference, which is 1 star. This tells you that GCD, the GCD mod 3 is actually equal to 0. That 3 actually does divide the GCD. Okay, so now we have our 3 cases. So in the first case, if you start with A being a multiple of 3 and B being a multiple of 3, you end up with a GCD that is not a multiple of 3. In the second case, you started with A and B, both of them were not multiples of 3, and you also ended up with a GCD that's not a multiple of 3. And in the final case, where you had one of your factors as a multiple of 3, but the other one was not, only in this case do you end up with a GCD that is a multiple of 3. So let's think about that a little bit and open up a new whiteboard here with a bit more space. What does that actually tell us? Well, it tells us if you have 2 multiples of 3, you end up getting 0. If you have 0 multiples of 3, you end up also with 0. But if you have 1 multiple of 3, this is a 1, multiple of 3, you actually end up with 1. This is pretty much saying that the operation f, the operation keeps the parity, the evenness or oddness of the number of multiples of 3 in the list of numbers that you have. Numbers of multiples of 3. And if you recall, we started with 1, 2, ... to 100. And you know, some quick maths again can tell you that there are 33 multiples of 3 in this range. And of course, 33 is odd, which is basically meaning mod 2 here is equal to 1. Therefore, based on this property, let's call this 3 star. By 3 star, we know that at the very end, we will also still have 1 multiple of 3. But at the end, we only have 1 number. So this tells us that the last number must be a multiple of 3. Is a multiple of 3. Big exclamation mark. But the thing is, we're not quite done, because we need to show that this multiple of 3 is unpaired. In other words, we need to show that 9 does not divide the GCD. So we could do this the same way as earlier by looking at how we might get 9 from 1 star, like either we have 9 only on one side or the other, or we get 3s from both sides. But instead, let's take this opportunity to look at how you might have approached the 2 functions plugged into the GCD originally in a direct fashion, as I alluded, maybe more experienced people would be likely to do. Here we have 4 cases again, but 2 of them are the same due to the symmetry, so 3 cases. Case 1, we have A mod 3 equals 0, and B mod 3 equals the 0. So we can write a equals to, say, 3x, and b is equal to, say, 3y. And then if we take a look at the first function that we plugged into the GCD originally, this a squared plus b squared plus 2, well, that is actually just going to be equal to 3x squared plus 3y squared plus 2. And that's going to be equal, just squaring the 3's here, you're going to get 9 times x squared plus y squared plus 2. And, well, this first part is obviously divisible by 9, so it goes away, and 9 does not divide 2. So 9 cannot divide this first function that we plugged in, and therefore 9 can't be in the GCD. Case 2, we'll do a mod 3 is equal to 0, but let's say b mod 3 does not equal to 0. So in this case, again, we can say a is equal to 3x. And this time, let's look at the second function that we originally plugged into the GCD, which is a squared b squared plus 3. Well, this is going to be equal to 3x squared b squared plus 3. And that's going to be equal to 9x squared b squared plus 3. And of course, if you're asking about can 9 divide this, 9 divides the first part since there's multiple 9 here. And 9, of course, does not divide 3. So since 9 does not divide the second function, again, it cannot be in the GCD. And finally, we have our third case, which is a mod 3 does not equal to 0, and b mod 3 also does not equal to 0. Well, we're going to, once again, let's take a look at this a squared b squared plus 3. And, well, this, if we look at this mod 3, of course, this plus 3 turns into a plus 0. But since both a and b are not multiples of 3 here, by Fermat's little theorem, we know that this is basically just going to be 1 times 1. So that's going to be congruent to 1 mod 3, which tells us 3 does not divide this second function here. 3 does not divide a squared b squared plus 3, and of course that means also that 9 cannot divide the second function. And because 9 does not divide the second function, it can't be in the GCD. And that's all your cases. And since in every single case we had that 9 does not divide the GCD, 9 does not divide the GCD, and 9 does not divide the GCD. So in altogether, 9 cannot divide the GCD. That finally tells us that 3 divides the last number, but 9 does not divide any of our GCDs. And since the last number is a GCD that we got from one of our operations, it's going to look something like this. Last GCD is going to be equal to some p1 prime to, say, x1 times dot 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 pm to the xm, and then we're going to have some 3 to the y. But since we know 9 does not divide the GCD, the power of 3 at the end, well, it has to be equal to 1. And of course, 1 is odd. But for a number to be a square, all the powers have to be even. So we've now shown that the last number is not a square. which was our goal all along. And then we can add a square, and we're done with the problem. If you are still set on looking at problems that are mod 2, but you like the sort of problem-solving concepts that were in this problem, I have a problem to recommend, which is this string reduction problem that got shared to me from UCI. I didn't go to UCI, but a few of my friends did. They shared me this problem from a long time ago. So I'll link it in the description below. You can take a look if you're interested. And finally, I'm going to leave you guys with 2 challenges. The first challenge is, can you change the functions in the range so the unpaired prime that you find at the end is any prime that you want? And the second challenge, which will be pretty easy if you solve the problem the way that I explained today, prove that if a and b are equal, then the GCD for a squared plus b squared plus 2 and a squared b squared plus 3 is equal to 1 if a and b are even, and 4 if a and b are odd. The hint I'll give is, for the 1 case, try adding and subtracting some term, like maybe 4n squared or something like this. Try thinking about this. If you get stuck and you're trying to look for a solution that doesn't involve the that sort of factor difference, which is 1 star. All right, that's pretty much all I have. Hope you guys found this interesting, and see you in the next one.